All right, so last time we had class was quite a while ago because we had the snow days, then we had the double A week before that. So that's why I reviewed a few of those things we're going to need in 5.4 part 2. So last part of chapter 5 we're doing today. This is going to finish up the algebra part of this class. Okay, so basically we've studied every kind of function except trig. Right? We haven't started anything with trig. And that's what chapters 6, 7, and 8 will focus on. All right, so this is kind of the last part of stuff we're going to look at that's not trig for quite a while. Okay, so the first thing we're going to do is we're going to solve an exponential growth or decay problem algebraically. The problem I'm about to give you, you've already done. We did it graphically. All right, so we'll just try to remember how we did it on the calculator. But what I really want to focus on now is how to do it with algebra. All right, and we've learned everything we need to do it at this point. All right, so here's the problem. We've got a town with an initial population of 50,000 people growing at 2.5% every year. How long before we reach 100,000 people? Or basically, how long for us to double? Okay, and I think the section we did this problem in was 5.1, when we talked about exponential growth and decay. So the fact that they tell you it's increasing at a certain percentage every year, that tells you that it's exponential. Okay. Whenever something goes up the same percent over and over and over, that's exponential. Now, is this exponential growth or decay? We know it's exponential because it's the same percent every year. But what word here tells you it's growth or decay? Yeah.
Increases.
It's increasing. That's growth. Exponential growth. So what I need is my formula for exponential growth. I'm going to plug everything in, and then we'll solve it. So I'm going to call my formula P of t, population as a function of time. So t will be my variable that I use. Happy face. All right, so P of t. All right, can someone remind me, what's the first thing that you write in the exponential growth formula? Yep.
Like beginning.
Yeah,
the 50,000.
The initial amount. So you start with initial amount times, and what goes in the parentheses? Chris?
0.025.
0.025, and one other thing. So that's going to go over here.
What's it like? Minus t?
Yep.
Plus 1.
Plus 1. So it's p times 1 plus r. And then the exponent, in this case, is going to be what? It's our, think back to the formula I had. Yep.
0.025.
So we've already used the 0.025, so that's done. But I don't have my variable yet. So, yep.
Would the exponent be 1? Or no?
The exponent, that's always your variable.
So just be t.
T. So remember, the formula is p times 1 plus r to the t. You know the p, you know the r. You don't know the t. That's the question. How long will it take? We're going to solve for that. Okay. What else in that word problem haven't I plugged into that equation yet? One more thing. Yeah? We haven't filled in the 100,000. Brandon, where is that 100,000 going to go?
I don't know.
Well, what is the 100,000? It's 100,000 what?
Like people?
People, right? It's not, is it 100,000 years?
No.
No. So it's not going to go in for the t because it's not a time. It's going to go in for population right there. Okay. So fill that in. So 100,000 equals 50,000 times 1.025 to the t. Now, if I was going to solve this graphing, can someone remind me how we would have done this, just graphing it? And we did this back in section 5.1 a long time ago. Yep.
Put the right half in for y1 and put 100,000 in for y2.
Yep. And then what?
Set your window so you can see it and then see where it intersects.
Exactly. You just find the intersect between y1 and y2. But now it's said to solve algebraically. So the goal is to get t by itself. Does anyone see one thing I could do on both sides to start to get some stuff away from the t? Yeah, you can divide each side by 50,000. That doesn't quite do it, but it's close. That's gone. 100,000 divided by 50,000 is 2. And then we have 1.025 to the t. So not a very complicated equation. The only thing that's a little lousy about it is there's a variable as an exponent. So what I would like to be able to do is put this t in front. But I can't just move the t in front. The only time you can move the variable in front is if what function is involved. Yeah? Logarithms. Okay? So if you had an equation like this, and you had to solve it, you can do the same thing on both sides to solve it. In that case, it would be to take the square root. Okay? Well, I'm going to do something up here. I'm not going to take the square root. I'm going to take the log of what's on the left, and I'm going to squeeze it in, the log of what's on the right. I did the same thing on both sides, just like taking a square root. That's okay. But now, what we can do is you can take the t and move it in front of the log. Okay. So now you can write t times the log of 1.025. So we took the t and we moved it in front. Now what we have here is basically a number equals a letter times a number. So all I want to do is move that box next to t to the other side. So when you have a number right next to a letter, what operation do you use to move it to the other side? Yeah. Divide. Yeah, divide. And that's going to be our answer. So we're going to divide by that number. Doesn't matter what the number is. In fact, I'm never going to find out what the log of this number is in the whole problem. What I'm going to find out is what this number is. That whole thing. T equals, and I'm going to divide that all out. And that's going to be my answer. All right, so let's see what we get. So log of 2 divided by log of 1.025. Now, what was I careful about when I typed that in? I didn't even mention it, but I've mentioned it before. What do you got to be careful with? Yeah?
Parentheses.
You got to be careful with parentheses. If you forget the parenthesis after the 2, it will come out wrong. Okay, so make sure you type it in just like that. And we get about 28.07 years, which I remember when we graphed it, because I've done the problem several times. That is what you get. So if you look back in your notes from 5.1, that's what you'd have. 28.07 years. And that's it. So, not too bad to solve an exponential equation by hand. Basically, it involves a division, taking a log of both sides, which allows you to put the exponent in front, and then another division. And that's it. pretty much every time. Any questions on that? Okay, other thing is, notice I didn't do any rounding till the very end. I didn't take the log of 2 and round that, and then the log of 1.025 and round that, and then divide them and round it again. I typed it all in once, and I rounded once, and that was it. All right, so as far as really calculating something by hand, that's it for 5.4 part 2. The other thing in part 2 is on the calculator. All right, so in Algebra 1, even in like statistics, sometimes you have a set of data and you want to find a line that fits the data. Like let's say maybe you have this. That line isn't perfect, but it's a good approximation of the trend that's happening. Okay. Well, that's good if your lines look like, if your points are pretty much in a line. If you had something like that, that would not be a good set of data to try to fit a line to. How come? How come a line's not a good fit there?
You're missing one of the points.
What about the points? Why
all over the place, so a straight line wouldn't hit like even half of them.
Yeah, those lines aren't, those points aren't in a straight line. They're more of a curve. I would say you'd want to find a curve maybe like, well, maybe even a little bit more like this. That's a better fit to the data, right? A curve, right? There's all kinds of curves you can do. We're going to look at one specific kind of curve you can do on the calculator called a power function. Okay, we're going to find what's called a power function. So a power function can look something like this. That's an example of a power function. It's a single term. There's two things you have to find in the power function. You have to find A, and you have to find M. And you can do it by hand. It's not something that we focus on in this class, though, how to do that. I'm going to show you just how to do it using your calculator. Now, when we find A and M, I think the calculator, or your calculator, if you're using one of mine, might call those two letters something different. It doesn't matter what you call them. Okay. The point is, you just have to find them and fill them into the formula and get a final answer like that. That's what you have to find. Okay. What I wrote right there, that is not the answer to this problem on the left. I just made up 2x cubed. That's just an example of what a power function can look like. The number for A is 2, and the number for M, and that one was 3. All right, hold off on 1 second. All right. So we're going to find a power model for this data. The first part is basically determining whether or not you should use a power model, because a power model isn't the right tool to use all the time. It's not. It's the right tool to use some of the time. Okay. For you guys, I'm just going to give you a set of data and say find a power model. I'm going to give you a set of data that a power model is the right tool to use. So you don't have to worry about the determine part. We're not going to do that. So here, the directions are just going to be find a power model for the data. And that's how it'll be if I was going to give you a test. That's what it would say. Find a power model for the data. Okay. So as I go through this, you may want to take a few notes or write something down. I'm not going to detail every single step. It'll be in the video if you need it. But you just might want to write a few key things down on how to do it. Okay, so first thing we have to do is we have to get all those numbers in the calculator. Okay, so we have to type them in a table. Now, one thing people mix up is there's two different tables on the calculator. You can go second table and you can look at stuff there. That's not what we need. Okay? Second table is used when you're graphing stuff. Okay? We're not graphing anything yet. We're typing in data points. So to type these data points in, you want to press Stat, and then the first option you will see is Edit. You're just going to pick option 1. So Stat, Edit, option 1. That's the table that I want you to see on the screen. Now, if somebody has used the calculator like on the last test, they may have already typed in some numbers there. So let's say you had numbers like that, and you want to clear them out so you can type in a problem. This problem might even be typed in, but maybe it's not. It's hard, I'm not sure. Does anyone have it typed in already? No. Okay. So if you have other numbers because someone else has used it, just highlight the number, press delete. In fact, if you just highlight the top number, you can just keep pressing delete. Don't press delete on L1, because if you do that, what's going to happen is now I've just deleted the entire L1. Right? And the only way I know how to get it back is to go second, memory, and now I have to reset everything on the calculator. There's probably another way to get it back besides doing that. Now if I press Stat, Edit, I have L1 back. So if you accidentally delete it, you can get it back. Now, what you want to do is put the X's in L1. 1, 3, I'm just hitting enter each time. Just like that. 1, 3, 5, 8. It's easy to do all the X values first because that's how the cursor moves. It just goes right down the column. Now, you're going to press the right arrow and you're going to put the Y's in L2. So 5, 31.2, 73.1, and 160. It is important that you have the same number of X values and Y values. If you don't, it's like writing a coordinate and leaving a number off. You can't. You've got to have an X and a Y for each row. Now, notice here there's L3, L4, L5, L6. It keeps going. I'm using L1 and L2 because if you do that, it's easier. If you used L3 and L4 or L1 and L5 or any two, it's okay. But it's easier if you do it the way I just did it. Okay, any questions on typing that in? Yeah?
My calculator's kind of different, but I can ask you after class.
Yeah, on the Inspire, I've never done it. I'm sure we could Google it and figure it out, but I've never done it on that one.
Okay.
So you can use one of mine, or you can try to figure it out on yours. It's up to you. Okay, so we got our data points in. Now it's automatically saved. You don't have to do anything else. Now you're going to go to Stat again, but this time we don't want to edit. We're going to calculate something. So now you're going to go to Calculate. And what we're going to do is calculate what's called a regression equation. And there's many kind of regression equations. There's quadratics, there's cubics, there's quartics. What's the degree on a quartic? Yeah? Yep, 4th degree. So that's like a 2nd degree polynomial, 3rd degree, 4th degree, all kinds of different things. We're looking for what's called a power regression. On my calculator, it's option A. We're going to find a power model that fits this data. So once you get Stat, Calc, pick option A, and you hit Enter. Don't hit anything else yet. That's what it should say on your screen. It should say, okay, I'm going to assume you put the X's in L1, and then you put the Y's in L2. That's exactly what we did. If you didn't, let's say you put the x's in L3. You could press second 3 and change the calculator and say my x's are in L3. But that's why I told you if you put them in L1 and L2, you don't have to change anything. So second L1. Okay. Nothing you need to change there. All you have to do is highlight, calculate, and then hit enter. Okay. And a lot of times when you do a power regression, if the data is pretty close to a curve, you're going to get numbers that almost look like they should be something, but it's like the calculator rounded them. Like, look at A, for example. What do you think A should be? Yeah? 5. Yeah. So A is 5. And B, if you wanted to think of it as a fraction, you've got the same decimal repeating 5 times. So if that number just kept repeating, what would B come out to as a fraction? Yep.
1 2/3.
It's 1 2/3. Okay. So the calculator tells you what it's calling the letters. Here's the formula. I think I use the letter M, they use the letter B. It's the same difference. Y equals AX to the B. A was 5, and we're going to fill these in a second. And B is 1 2/3. Or if we write that as an improper fraction, 5/3. Now using those numbers, just write your final answer. Y equals 5x to the 2/3. So if you were to graph that equation, which I will in a second, it should go through those points perfectly. 5/3. Thank you. Okay, so just using the calculator to figure out those two numbers. Okay, let's graph those points. I mean, at this point we're done, right? But I just want to check and see. Okay, is that really a good equation? How good is it? Let's see. Okay. What's our lowest x value in that list?
1
1. So let's go to 0. What's our highest?
8
So 10 is okay. What's our lowest y value?
5
5, so let's go 0. And what's our highest?
160
160, so let's go like 180. Okay? And now what we have to do is turn on one of our scatter plots. Okay? So once you set your window, press y equals, like you're going to type in an equation. But don't type anything in for an equation. Go up to plot 1 and hit enter. What you just did is you turned on a scatter plot. So by turning on the scatter plot, the calculator should now graph those points. So I'm going to hit graph, and there's the points. Now, depending on if somebody has changed some settings on your calculator, you might see little dots instead of little squares. Different things could happen. Did anyone have trouble getting those to come up? I mean, you can also, if you press second stat plot, see how it says plot 1 is turned on? That's the one I just turned on. And it's using, if I hit enter, it automatically uses the x's from L1 and the y's from L2. If you didn't use L1 and L2, you'd have to change it. I can also change the type. I can make it connected. I can make like a bar graph. I can make box and whisker plots. I can change and do all kinds of things. Change the colors, but I don't want to change anything. So if you press y equals and highlight plot 1 and hit graph, that's what you should get. Now I'm going to type in my equation and see how good of a curve did I just find. So let's type it in. 5x to the 5/3. So looking at the curve, how good of a curve do you think that is for to fit to our data?
Pretty good.
Yeah, just about as perfect as you can get, right? Now, depending on the data, like if you did an actual experiment in like science or something, your data might not be perfect. So if your data is not perfect, the curve isn't going to be perfect. But the calculator will find the best curve possible. So what's the advantage now of having the equation for this curve? What could I do now that I know the equation that represents that data? What could I use this equation to do? Yeah?
You could like figure out where another line intersects it.
Okay, let's think of it in terms of, let's pretend that x is minutes and y is the number of bacteria. So after 3 minutes, you've got about 31 bacteria. After 8 minutes, you've got 160 bacteria. But now I have this equation. So what could I do with this equation now? In terms of like what I just said. Yeah.
You could use it to calculate how long it would take for there to be however many bacteria.
Yeah, I can do all kinds of things. I can say, somebody says, well, what about tomorrow at this time? How much bacteria are we going to have? So I could say, all right, 24 hours from now, I could plug in 24 for x and see what I get. So I could predict how many bacteria I'll have in the future if this pattern continues. We don't know the pattern's going to continue, but if it did, we could figure it out. Or we could do it like Jared said. You know, once we reach 200,000 bacteria, that's the limit. We don't want to go any further on the experiment. So when should we shut it off? Okay, when should we kill the bacteria? So if you want to know when to reach 200,000, that's kind of like the problem we just did with the population of the town. Just think of the bacteria as a population. All right, so any questions on how we did that? Okay, not hard, as long as you know what buttons to press and where to go. But everything is under stat. You go to edit at first, and then you go to calculate and power regression. When I have you guys do a review on Monday, I might have you try like a quartic regression or a cubic or something else, but the steps are exactly the same. Okay, so any questions on finding a power model for data? Okay. So last thing. So every time we study functions, we always look at two things. We look at how could we solve an equation, and then we look at how could we draw it. Well, this is the drawing part. Okay, we just looked at solving some equations a little bit in the last section, the first problem we did. Now we're going to look at doing some sketches. So if you remember back from a couple weeks ago, there's only two types of logs that the calculator can give us. Does anyone remember ln? What was the base on that log?
10.
That's the base on this one. That's base 10. While we're talking about base 10, I'll come back to the other one in a second. Does anyone remember what base 10 is called? It's the, yeah?
Natural log.
That's the other one.
Oh.
Common log.
Oh.
So you've said everything for the other one. So base 10 is your common log. Base E is your natural log. Other than base 10 and base E, there's no buttons on the calculator like if you wanted to do base 3. There is no button for base 3. There's base 10 and there's base E. So, using those two buttons, we can type in any base that we want. And this is basically how you do it. I'm actually giving you two ways to do it. This is way one. This is a second way. Personally, I would just remember one of the two. They're exactly the same. So let's say you wanted to do like log base 2 of 6. And you wanted to figure out what that is. You don't have a button for base 2. But what you can do is use this formula. X is always the number in the top. B, think bottom. B is always the number that goes in the bottom. So if you wanted to figure out log base 2 of 6, this is how you can type it in. Log 6 divided by log 2. Now notice my calculator didn't even put the 10. That's okay, doesn't need to. If there's no base written, it's always a 10. Or, if you prefer to do it with ln, you can do the same thing that way. You're going to get exactly the same answer. What's important though is that you have to put the 6 in the top, and you have to put the 2 in the bottom. I think this number was higher, so it goes up higher. This number was lower, so it goes down lower. Right? So that's the change of base formula. Any question on it? Okay, you don't have to know both. 1 or 2 is sufficient. Either one. Okay, so they want us to graph that. And then once we graph it, look at the stuff we always do. Domain, range, stuff like that. Now, is that a base that the calculator can do direct? No. What is the base? Yeah.
3.
It's 3. So if we're going to type that into a calculator, we're going to have to rewrite it as a fraction. Can somebody give me one way? You don't have to give me 2 ways. Just give me one way to rewrite f of x so I can type it in on a calculator. Yeah.
ln x
Yeah.
over ln 3.
Perfect. If you want to graph this, you need to type in that. At least that's one of 2 ways you could do it. So let's graph it and see what we get. Well, I'm going to do 2 things. I'm going to clear the equation that I had in there. I'm also going to go to plot 1. I'm going to hit enter, and I'm going to turn it off so I don't keep seeing those dots on the screen. Okay, so ln x divided by ln 3. Let's do zoom 6 to put it back to normal. Now, that picture is a little bit misleading. Can somebody remind me what really should be happening there? But the calculator can't quite do it, yeah?
It's almost like straight down, but it never actually hits the 0.
Yeah, it's an asymptote. It really should look like this. Okay, that part should just keep going down. And if you want to check that, I mean, you look at the graph, to me it looks like it stops at -2. Well, go to your table and type in, since I reset the memory on my calculator, I need to put a few things back the way they were. Type in 0.00000001. You get -16. That graph is definitely not stopping at -2. It's going down forever. Okay, so that kind of answers part of this question. What's the domain of that graph? Think left to right. Yep.
Parenthesis.
Yep.
To infinity.
Parenthesis
0.
0 to infinity. Perfect. Just like Brandon said, it never reaches 0. You can try 0. Put it in your table and watch what happens. You're going to get an error. You can't take the log of 0, and you also can't take the log of a negative. That's why it's 0 to infinity. Now, how about the range? Think about how far down and how far up. Yeah.
-infinity to infinity.
Yeah. It does go down forever, and it does go up forever. Just not very fast, but it will keep going up. And if you're not sure, check a big value. All right, it's at 3.5, and now check an even bigger value. One above 3.5, right? And then check an even bigger value. It's just going up. Extremely slow, but it's just going to go up forever. Okay. So any question on the domain and range? Okay. So all the transformations that we've studied all year still apply to logs. Okay, the A, the B, the C, and the D. Okay, I don't want to spend a super long time on them because we've done these a bunch. But can someone remind me what the A would do? Yeah. The D, that's going to be the D. That'll be the D. Jared?
That'll move it left and right.
Yes, that's a horizontal shift. All right. How about the B? What's the B? Yep.
So, horizontal stretch.
Yep. Stuff inside parentheses is always horizontal, and it's always backwards. Plus would shift it left, minus would move it right. Adding or subtracting is always a shift, multiplying is always a stretch. So what about C? It's multiplying, Eric?
Vertical stretch.
And it's outside, so there's your vertical stretch. That's adding, so it's a shift, but it's outside the log, so that's a vertical shift. What if B or C was a negative? What does that cause to happen? Chris?
Flip.
Causes a flip. Either a horizontal flip, if B is negative. So remember, a horizontal flip would mean something like this. That's a horizontal flip. Or if C is negative, that's a vertical flip. That's a vertical flip. Okay, so let's take a look at that function. There's not a lot of transformations in it, just one. And I want to find the domain, range, and vertical asymptotes. So first thing is we'll just describe what's happening. Okay, out of the A, the B, the C, and the D, which letter have I changed? Yeah? Here?
X or B.
The B. I've altered the B. Now, if you wanted to think of this, what number is in front of the X, really? It's technically a 1. So I haven't really done a horizontal stretch. All I've done was make the B negative. And we just said what happens if you do that. So if you make the B negative, what kind of flip is it? What's it?
Vertical.
Is the B inside or outside the parentheses?
Inside.
Inside. And the stuff on the inside is always
Horizontal.
horizontal. So it's a horizontal reflection. All right. So to graph y equals log base 3 of negative x from the original, log base 3 of x, do one thing. Horizontal reflection. So maybe I should say, do the following. Step 1, horizontal reflection. And that's it. That's all we got right. Now, domain, range, and all that stuff. Well, think about, if we know what the original looks like, we just graphed Where is it? We just graphed this one. So imagine that picture flipped horizontally. That'll help you figure out the domain, the range, and all that stuff. It's basically going to look like this. That's a mirror image. So what's the domain going to be of this graph now that we flipped it? But yeah. Yep, negative infinity to 0. Now, how about the range? You can't really mess up the range of a log function because it never changes, yeah? Yeah, no matter how you flip it, shift it, stretch it, the range is always negative infinity to infinity. Now, the vertical asymptote. When you write the equation of a vertical line, does it start out x equals or y equals? Yep. X equals. And did the vertical asymptote in that graph move compared to that graph? No, it stayed exactly the same. So the vertical asymptote is x equals 0. If you put y equals 0, you just wrote what kind of line? Y equals is y, yeah.
A horizontal line.
That's a horizontal line. There are no horizontal asymptotes here, right? They vertical, you got to write x equals. Okay. Any questions on that? Okay, so we're not going to spend a ton of time on the stretches and shifts because we've done a lot of that. All right, let's look at, this time I don't want to know the domain, the range, I just want to know the transformations. What's kind of weird though about that? Look at what they're having you graph and compare it to what I wrote up above on the page on the left. Something's off. Yeah. Yeah, we usually like to put the x first and then the number without x second. So this is the same as, what could I put inside the parentheses instead of 3 minus x? Chris?
Yeah, but negative x plus 3.
Yep. And now, Jacob, how many transformations are happening there? 2, yes. And if you're not sure what order to write them in, look at the A, B, C, D. Do them in that order, alphabetical. So what's the first thing that's happening here? And you've got to be specific about the direction. Chris?
Horizontal flip.
I agree that we are going to have a horizontal reflection or flip, but that's B. There's something we have to do before that. So I'll write that one second. So horizontal reflection. What do we have to do before that? Jerry?
Horizontal shift 3 units left.
3 units left, yes. So shift 3 units left. As long as you tell me how much and which way, you're good. If you just said shift 3 units, that's not enough. If you said also shift left, that's not enough either. Direction, how much? Remember, plus always goes left, minus always goes right. For vertical, positive is up, negative is down. Vertical is normal. B is also the opposite of what you would expect. If you put a big number in for B, like let's say you did this, that's not going to stretch it by a factor of 5. That's going to compress it. Bigger numbers make it smaller horizontally. Smaller numbers like 1/2 or 1/3 make it bigger. That's always been the rule with horizontal. It's always the opposite. Okay, any questions on how we got those two transformations? Yeah.
So how do you know which one comes first, the shift or the reflection? Does it matter which one you do?
Yes, always go in order of the A, the B, the C, and the D. So follow alphabetical order. Horizontal shift, horizontal stretch, vertical shift. If you have a reflection, just do it when you would do B and C. It doesn't matter if you do the stretch or the reflection, or switch that. Stretch, reflection, reflection, stretch. That's the same. But everything else, you have to follow that order. All right, so last two things we're going to look at is graphing, and we'll look at one word problem, and that'll be it. Now, I mentioned, and the book mentions this, when you want to graph a log function, it's helpful to find the intercepts and the vertical asymptote. I definitely agree with this one. That's important. Because once you find the vertical asymptote, your log function is going to go right up against it, and it's going to bend one way or the other. It's either going to go like this or like that. But intercepts, go back and look at this graph. You might not always have a y-intercept. This graph doesn't. You will always have an x-intercept, guaranteed. Because we've said that these graphs go up and down forever. And they're continuous. You don't lift your pencil when you're drawing. So if you go up and down forever and never lift your pencil, you're going to cross the axis somewhere. But you might never cross the y-axis. So when I say find the intercepts, maybe, if it has one. But this one, it will always have. All right, so vertical asymptote, always something you want to find. And the way you find it, do I have an example on the next page, or no? Well, I'll use this one. The way you find the vertical asymptote is you drop your pen. You take your argument and you set it equal to 0. What I just circled, that's the argument. It's the stuff in the parentheses. This is the only stuff that has anything to do with the vertical asymptote. The stuff in the parentheses. Okay, so if I wanted to find the vertical asymptote of this one, I would go like this. So if I was going to sketch this, it would have a vertical asymptote at x equals 3. You don't have to sketch this one. We're going to sketch a different one. Okay. Remember, the x-intercept is when you plug in 0 for y. The y-intercept is when you plug in 0 for x. And if you need more points, which I usually do, use your calculator and plot a couple more. I mean, I would say if you've got 5 points like that, that's going to be pretty good. You can find as many points as you want, but at this point, you guys know how I grade graphs, and I'm not looking for it to be perfect. I'm looking for it to be, pretty reasonable. Now, if the graph is supposed to curve to the right and you draw it curving to the left, well, now you've drawn it completely backwards. That's different. But just get a few points in there and sketch it, and that'll be good. Remember, though, you cannot take the log of a negative number, right? So like if you had a problem like this, don't plug in 1 for x. That's not going to work. If you plug in 1, you're going to end up with the log of a negative number. Pick numbers bigger than that. Pick numbers like 3, 4, 5. Okay? Got to make sure that the argument comes out positive. Okay, so let's make a sketch of this graph. Now, the asymptote, we're going to find the asymptote to make the sketch. So that's not going to be an extra step. Can someone remind me, how do I find the vertical asymptote? Take what and do what? Chris?
Take 3x plus 5 and equal to 0.
That's it. Take 3x plus 5, set it equal to 0, and solve it. Now, since we're graphing, a decimal is kind of handy here rather than a fraction. What's negative 5/3 if you were divided out? Okay. Yeah, negative 1.67, roughly. It's like negative 1.6 repeating. So I'm going to draw a vertical line at negative 1.67. That's the first thing I'm going to do. So let's get a graph. And we'll put a vertical line at negative 1.67. Yeah, I'll make it dotted so we know it's an asymptote. About right there. Now remember, your function is either going to bend to the right or it's going to bend to the left. It's never going to touch that dotted line. Okay. Let's think about numbers we could pick for x in terms of numbers either bigger or smaller than that number. Could you pick a number like, let's go way smaller, let's go negative 10. Could you plug negative 10 in for x? Negative 10 would be to the left. What would happen if you plugged in negative 10 for x? Yeah?
You'd get a negative.
Yeah, you get a negative 25. That's no good. You can't take the log of negative 25. Right? So this graph, you're going to have to pick numbers bigger than negative 1.67. Okay. So let's type that in and use the table to get some more points. So I'm going to type it in as log 3x plus 5 divided by, and what's going to go in the bottom? Yep. Yep. Log parenthesis 2, second table. All right. Let's do 0, 2, 5, 7, 10. I just picked random numbers. You do not have to use those exact numbers. I use 0 because that gives me my y-intercept. 2.3. 2, just under 3.5. And hopefully now we start seeing it level off. 7, we're at 4.7. 7, 1, 2, 3, 4. 0.7. Then I did 5 too. I guess not. 10, 5.1. 1, 2, 3, 4, 5. Anyway, that's good enough. I can see what's happening. So your graph is going to do something like that. Remember, getting closer and closer to that dotted line, but never touching it. And that's it. That's how you make a sketch of a log function. You can always double check it on the calculator, but remember the calculator is going to have trouble with it. So the calculator is really only sketching this part right here. It shouldn't look like that. It should go down further. Very steep. Okay, so any questions on the graph? All right. So, last thing we'll take a look at is a word problem that has a log in it. And the formula we're going to look at, maybe you've heard of this or not, if you watch the news and they say like, you know, an earthquake of a magnitude 4.2 or something like that, that's on the Richter scale. Okay, so it measures how powerful an earthquake is. And this formula has 3 variables that you need to fill in for to find the intensity of an earthquake on the Richter scale. Okay, R is the magnitude. That's the number when you hear the news that they describe how powerful the earthquake was. These other numbers you don't really hear about. Okay. A is the amplitude of the vertical ground motion in micrometers. Okay. Amplitude of vertical ground motion in micrometers. T is the period of the earthquake wave. And if you're thinking, what do you mean wave? Well, imagine you took a rock, right, and threw it in the middle of a lake. Where that rock hits, think of that as like that's the center of your earthquake. From that point, a wave comes out. Like that. Well, exactly the same thing happens in an earthquake. The ground moves as a wave. Well, the period of the wave is basically the distance from, here's one period of the wave. We're going to study that a lot more when we get into trig. But that distance from here to here, that's called the period of the wave. Some waves are very long, some are very short. Drop a rock in the pond, the waves are very close together. In an earthquake, I mean, the waves could be hundreds of feet long, huge waves. And the ground is moving like a lot. And then B is a factor that accounts for the weakening of the wave. So where the earthquake happens would make a big difference. Think about like if you drop a rock in a sandbox. Most of the energy of that rock is just absorbed right into the sand, and the wave doesn't spread out very far. Maybe a little bit, you get a crater, and that's it. But in water, the wave just keeps going for a while, because the water doesn't absorb the energy quite like the sand does. So B is a factor that accounts for how the wave weakens over time. Okay, so any questions on the formula? Okay, let's try an example. Let's see. All right, so let's find the magnitude of the following earthquake. All right, and they tell you A is 275, T is 2.5, and B is 4.25. I forgot the letter I used for intensity. I use R for Richter scale. Okay. So what's the first thing I write down in my Richter scale formula? Yep.
10. Or, well, the 10 and then the parentheses.
A 10.
Did I write that down wrong? You go back. Log.
Log.
I wrote that wrong.
It's a log. And Brandon, what's the first thing in the parenthesis?
It was a fraction. I don't remember what it was though.
So the first thing is
Over T.
A over T. So what would I write in this case?
You write 275 or 2.5.
And Eric, what else do I need there?
You need the B
Yep. And how do I put that in?
all the way to the right, and it's plus 4.25.
4.25. Okay. So let's see what we got. Now it's a log with no base. So what base are they assuming? 10. Yeah. So let's go log 275 divided by 2.5 plus 4.25. All right, so that's about a magnitude 6.3 on the Richter scale. Let's see what that really means and how powerful is that. So, I don't know if you can do that or not, it's kind of small. But, so it says basically how many of them you get a year and then how severe they are. So a 2.5 magnitude, sometimes you don't even feel that, but a device called a seismograph would pick it up, and there's about 900,000 of those a year. So our magnitude was what? 6.3. So that says may cause a lot of damage in very populated areas, and usually there's about 100 of those earthquakes a year. So that's pretty powerful. I don't know what this magnitude class is. Well, I guess ours would be considered a strong earthquake. So pretty strong, but I mean not totally destroying everything like magnitude 8. Now, the other thing is when you look at the Richter scale, like let's say you have a magnitude 6 versus a magnitude 7. You might say, well, not a big difference, 6, 7. Well, the way the Richter scale works, since the formula is based on a log, each time you move one number to the right, it's 10 times more powerful. So like, if you compare a magnitude 2 to a magnitude 4, it's only 2 numbers away. But how many times more powerful is it? Yeah? No, times 10 times 10. 100.
Oh, 1.
So every time you move one number over, it's 10 times more powerful. So magnitude 5, magnitude 7, what's the difference? 2 numbers? The difference is a magnitude 7 is 100 times more powerful. It's a big difference. If you've done, has anybody done pH in chemistry? Acids and bases?
Yep.
Acids and bases in chemistry work exactly the same way. All right, so homework tonight will be page 293. That's the first part we did with the using the calculator and that part. And the second part is page 301. And that's on graphing logs, and I think there's one problem in there with the Richter scale.